Hello, I am Dr. N.B. Hulle. In this particular video, we will try to understand the transient response of RL series circuit for source-free circuit. That is nothing but there will not be any source after the switching. Source may exist before the switching. Here, for the analysis of the transient response of the first order system for the circuit which does not consist of the source after switching, that is source-free RL series circuit. Now here in this case we will consider this figure. In this case the switch is in this position number 1 before switching and source is connected, and after switching we will shift the switch in the position number 2. Now here, as I discussed in the previous case, we will analyze the circuit into the two parts, that is behavior of the circuit before switching. Now here before switching the circuit was in the steady state with the position 1, and whenever it is in the steady state, this inductor will be replaced by the short circuit as I have shown here, and remaining circuit elements will be the same. Now here in this case, if we are applying the KVL and if we are trying to find out the initial condition of the network, that is condition before switching. In this particular case, IF0 minus is very same as IF0 plus. From this particular circuit, it is total voltage divided by resistance, that is V upon R, which is equal to its current, that is IM or maximum current. This is the current available in the circuit before the switching. That's why this is known as the initial condition of the network, that is before switching. Now, after switching, we want to analyze the response of the circuit or transient response of the circuit after switching. That is, after switching is nothing but for t is greater than 0. In that particular case, the switch will be in the position number 2, and whenever it is in the position number 2, no source will be exist in the circuit. Now here in this case, this is R is in the circuit and L is the inductor. Now here, the circuit was in the steady state before switching, and the inductor is charged to its maximum value, which is nothing but the IM. Now if we will apply the KVL to this circuit, now here in this case, according to the direction of the current, this will be plus terminal, this is minus, again here it will be the plus terminal, and this will be the minus. If we are applying the KVL here, if we are traveling in the clockwise direction, that is positive to negative, which is minus, here minus, the voltage across the resistance is nothing but IFT into R. Similarly, if we are traveling in the clockwise direction, again positive to negative, which is minus, and voltage developed across this inductor will be L into di by dt, and which is equal to 0, because after that there is no element in the circuit, and we will treat or we will assume this equation as equation number 1. Now again we will rearrange the terms of this equation. We will shift or we will multiply by the minus sign, then it will be L into di by dt plus it is R into I of t, which is equal to 0. Again here we want to make this circuit in terms of the time constant, that's why we will divide by R, means it will become L by R di by dt plus it is I of t, which is equal to 0. This is the equation for this case. Now if we will analyze the circuit further, we are separating the variables, that is L upon R, di of t upon dt, which is equal to minus I of t. Here in this case, this I of t we are shifting to the next side, that will become minus. In this case, if we are separating the variables, this is di upon I of t, which is equal to minus R upon L into t, and if we are taking its integration is nothing but the differentiation of the denominator is available in the numerator, that's why log of denominator will be its integration, that is log of I of t is equal to, on the right hand side, minus R by L is the constant, and integration of the with respect to t is not dt is nothing but t, and plus some constant of integration, that is the k, and we will name this equation as equation number 2. Now here we will find out this value of this integration constant from the initial condition of the circuit, and in this particular case the initial condition of the circuit is at t is equal to 0, IF0 minus or IF0 plus is very same as its maximum current IM, which is nothing but it is V upon R, as we discussed in the equation number 1. If we are finding the value of the integration constant, if we are substituting t is equal to 0, here log of I of t, and I of t is nothing but t is 0, I of 0, log of I of 0 is nothing but Im. Here this term will become Im, and in this particular case this t will become 0, means this whole term will become 0, and this is k, means here in this particular case we will get the term that is constant k is equal to log of im, and this will be the equation number 3. Now what we will do, we will put this value of this integration constant, which is log of im in this case, and we will get the next equation, and which will be helpful for finding the solution or finding the values for this source free RL series circuit. Now here putting the equation number 3 in equation number 2, we will get, if we are substituting that value, it is log of IFT is equal to, it is minus R upon L into T into, it is log of IM. Now here if we are shifting this log IM term on the left hand side, then it is log of IFT minus log of IM is equal to, it is minus R upon L into T. Here this is log a minus b is nothing but log a upon b, log of bracket IFT divided by IM, which is equal to this whole term, which is minus R upon L into T. Now if we are taking the antilog on the both side, we will get the final terms. Now here in this case, antilog of this particular term will be IFT upon IM, which is equal to e raised to power of minus R upon L into T. And here we can readjust this term R upon L as L upon R, which is nothing but the time constant of the circuit. But here time constant of the RL circuit is, it is L divided by R, means here it is expressed in the L upon R. In that particular case, the same equation can be expressed as IFT upon Im is equal to e raised to power of minus t by tau. And in this particular case, the expression for IFT is equal to Im into e raised to power of minus t by tau. This is the expression for current for source free RL series circuit. Now here in this particular case, if we are trying to plot the graph for this curve or this equation at t is equal to 0, if we have the time t is equal to 0, at t is equal to 0, e raised to power of 0 is 1, and in that case IFT will become Im, means graph will start from this point. This is Im. Now here we will put its another condition, which is nothing but t is equal to infinity. If we are putting the second condition, which is t is equal to infinity, in this particular case e raised to power of minus infinity, which is nothing but 0, and 0 into anything, that term will become 0, means finally at t is equal to infinity, this current is going to become 0. Here on this axis we have the current, which is IFT, and on this particular axis we have the time. Means this graph will be something like this, means it is decaying of the current, and when the time is tending to the infinity, the current in the circuit will become 0. That is the case in this particular case. Now here similarly we are interested in the calculation of the voltage across resistor and voltage across inductor for the source free RL series circuit. Again here I will prefer to use this general formula, because voltage across inductor is given by the formula L into di by dt, and the voltage across resistance is given by the formula, it is IFT into R. Now here if we are putting the value of IFT, here L is the term which is inductor, which is constant, differentiation with respect to t of its IFT, and IFT is nothing but Im into e raised to power of minus t by tau. This is very same as L into, if we are taking its differentiation will be minus 1 upon tau in bracket Im into e raised to power of minus t by tau. And if we are simplifying this equation, this will become minus L in bracket, it is 1 upon L upon R into Im into e raised to power of minus t by tau, because I am expressing this tau as a L upon R, because I want to simplify this equation further. Now here in this case, this inductor value is cancelling with this particular value, means final equation will be minus R into Im into e raised to power of minus t by tau, means voltage developed across inductor is minus Im into R into e raised to power of minus t by tau, means finally the voltage developed across inductor is, it is a minus V into e raised to power of minus t by tau. Now look at how is this minus sign, because the voltage developed across inductor is a VL, and it is given by expression that is L into di by dt. This is L into di of t into dt, or I will simply write it as di by dt. Di is the change in current. When this di is a positive value, in that case voltage developed across inductor will be the positive, and whenever this di is a negative value, the voltage developed across inductor will be negative. How is the case? I will take the case of charging of the inductor or source driven RL circuit. In that case, expression for the current is this IFT is equal to, what is the expression? This IFT is equal to, it is Im in bracket, this is Im into e raised to power of, or it is Im into 1 minus e raised to power of minus t by tau. It is minus t by tau is the expression for current whenever the circuit is source driven, and whenever the circuit is source free, in that particular case the expression for current is, this current is IFT, and this IFT is equal to, it is given by the expression which is Im into e raised to power of minus t by tau. Im into, it is e raised to power of minus, it is t by tau is the expression. It is minus t by tau. This is minus. Now here, if we are plotting both the curves, already I have discussed how to plot this graph. Here, if I am showing that, its graph will be something like this. It is decaying of the current. If I am trying to plot this curve, if I am trying to plot the curve with source driven circuit, at t is equal to 0, this term will become 0 because e raised to power of 0, and e raised to power of 0 is 1. 1 minus 1 will be 0. 0 into anything will be 0. This graph starts from this origin. And at t is equal to infinity, e raised to power of minus infinity is 0. 1 minus 0 is 1. 1 into Im is Im. Means somewhere here at t is equal to infinity. Means here graph is something like this. Now here, if we are finding the di in this case, in case of the source driven, this is final value minus initial value. Final value is larger, initial value is 0. Final value minus initial value, that is a di, will be the positive value. That's why the voltage developed across inductor will be the positive value. Similarly, if we are trying to calculate the similar value for this graph, here this is the initial value and this is the final value. In this case, initial value is larger and final value is smaller because it is decaying of the current or discharging of the value, in the discharging of the current. In this case, final value is 0 because I am talking about the current. The final value of the current is 0, initial value of the current is Im, means final value 0 minus Im, this current will be the di, which is the negative value. That's why the voltage developed across inductor will be the negative value. Now here, finally, I will come to this voltage across a resistor, which is R into IFT. Here, this is R, IFT is nothing but Im into e raised to power of minus t by tau. It is R into Im into e raised to power of minus t by tau, which is nothing but voltage developed across resistor is nothing but it is V into e raised to power of minus t by tau. This is the expression for voltage developed across resistance. Generally, the expression for voltage developed across resistance is very similar to the expression for the current, because in this case the expression for the current is I is equal to Im into, it is Im into e raised to power of minus t by tau. It is similar to that. Im into e raised to power of, it is minus t by tau. It is similar to that. And finally, the expression for the voltage developed across inductor, always I will prefer this general formula in place of this specific formula for this calculation. That's it about this particular video. Thank you for watching this video. That's all.